Okay, hello, we're back for part 3. We are going to prove that the limit of the product is the product of the limits. And this is the most difficult one of all, and this is the one that in every textbook I've ever seen that proves this. The proof is just a disgusting nightmare, and so I really think that we can do better. So this is the hardest one, but I think this is the one in which my proof is much easier to follow than what you will normally find out there. So okay, let's begin. Don't know how I'm going to fit this all on the board, but I think I can do it. There's going to have to be some erasing. Alright, well, yeah, first maybe let's establish this kind of lemma that we need. So, okay, I'm just going to call this a lemma, and here's the lemma. It's extremely obvious. Obviously true, but still we should talk about it. The lemma goes like this. If you take the limit as x approaches a of some function, and you get L, if that's true, then the limit as x approaches a of f minus L is 0, and also vice versa. Okay, so I want to show that this is true. Okay, I haven't actually thought about this in a long time. I hope this is kind of easy. Sure. Okay, so let's go. Let's first do the forward direction. So assume, I think this is really easy. So assume that the limit as x approaches a of f is L. Okay, great. Now I want to show that this limit is 0. Okay, so what is the limit as x approaches a of f minus L? Well, the smoothest way to do this now is to reach for the previously proved theorem that the limit of the sum is the sum of the limits. If the limit of the sum is the sum of the limits, then of course doesn't change any subtraction. Minus L is sort of like plus negative L or whatever. So by applying that limit of the sum is the sum of the limits, then I get that this is the limit. As x approaches a of f minus the limit as x approaches a of L. Limit of the sum is the sum of the limits. And what is the limit as x approaches a of f? Well, by assumption, it's L. And what is the limit as x approaches a of a constant? We already also proved that the limit as x approaches a of a constant, I don't know why I have a's all of a sudden, but it doesn't matter, then this is 0. Okay, so we're done. Now we go in the opposite direction. The opposite direction says assume, so from right to left, that's what that means. So assume that the limit as x approaches a of f of x minus L is 0, and then recover that the limit as x approaches a of f is L. Oh, okay, I know exactly what to do. Once again, I will apply the previously proved theorem, number 2, that the limit of the sum is the sum of the limits. So what I know is that the limit as x approaches a of f of x minus L is the limit as x approaches a of f minus the limit as x approaches a of L. But also, I've assumed that this is 0. So, that means that the limit as x approaches a of f minus, well, what is the limit as x approaches a of L? We've previously shown in class that the limit of a constant function is just that constant. And so now this is just a number, so the limit as x approaches a of f is L. Okay, good. In other words, if you feel like it, you may sort of move back and forth kind of fluidly between these kind of two statements. If this is true, then this is true, and vice versa. If this is true, then this is true. Okay, so good. having established that lemma, it's not obvious why we should care about that, but okay, there it is. I'm going to erase this now and begin. Okay. Whew. Yeah. So what are we trying to do? The limit of the product is the product of the limits. Well, yeah. Let me just think about my spacing for a second. Okay. Well, I guess it's kind of the same as before. Let the limit as x approaches a of f be L. Maybe I'm using C's now. And what does that really mean? It means that now I'm going to go back to using absolute values just kind of because. What that means is that for all epsilon greater than 0, there exists a delta greater than 0 such that for all x, if the difference between x and c is less than delta, then the difference between f and L is less than epsilon. Okay. Also, let the limit as x approaches c of g be m, and thus what I know is that for all epsilon greater than 0, there exists a delta greater than 0 such that for all x, if I am within if I'm within delta of c, then my function g is not too far away from m, specifically within epsilon. Okay, so this is all just background. Haven't done anything yet. What am I trying to actually prove? I'm trying to show that the limit as x approaches c of the f times g function is just Lm. That's what I need to show. Okay, so why should that be true? Well, yeah. Okay, here is where I pull a move. Following the lemma from 2 minutes ago, I've decided that instead of showing that the limit as x approaches c of f times g is Lm, let me instead show that the limit as x approaches c of f g minus Lm is 0. Okay? And not going back into the details, that's equivalent. So instead, I'm gonna prove this one. This is the one I'm gonna prove, and then that accomplishes the same thing. Okay, how am I gonna do this? Well, I need to get some kind of handle on this, right? What is the difference between f times g and Lm, right? I need to show that that difference is basically tiny, is kind of non-existent, right? I need to show that this limit is 0, so I need to show that this can be made, as small as one pleases. Alright, well, now we draw a picture. That's what we do. Yeah. So here's the picture. The picture tries to get some kind of geometric understanding of this relationship, this fg minus Lm thing. So okay, let me kind of do it down here. So what is going on? And why am I drawing a picture? Well, it's because like the very idea. Okay. Because I'm talking about the product of two functions. Like, what does that even mean? Like, what is the product of two functions anyway? Well, you're sort of, multiplying the two functions, which really just means you're multiplying their outputs. So, there's not necessarily any geometry going on, but if you want to understand it geometrically, you can think of multiplication as being the area of the rectangle with two particular side lengths. I think that's kind of helpful here. So let's do it. What is this? F minus L. Oh, interesting. Yeah. Okay. So this rectangle is kind of weird actually. Let me redraw it because it's not on my paper. It's kind of a little bit dumb to be honest. So okay. So I have some. Yeah. Well, I guess it doesn't matter. So I have some f. So this is f. And if I get near C, then f is supposed to be pretty close to L. So let's let this over here be L. And then, okay, but actually let's not stress ourselves out by trying to be in scale or anything like that. So let's let this be L, and then that makes this little piece here f minus L. Okay, and yeah, then let this be G, and so okay, let me just kind of complete this picture. This is going to be, say, m, and this is therefore going to be g of x minus m. Is this length here? Okay, I'm not so happy with the way this looks. So let me just write this. This is g of x minus m, cha cha cha, and it's kind of like that. Okay, so I have sort of a rectangle here, and the rectangle is like this. And what are the sort of values of all of these things? Well, the big rectangle, the whole thing is f times g. Okay, so that's the kind of the function that we're discussing. What is this rectangle? Well, this rectangle is L times g of x minus m, and cha 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 cha. This rectangle here is like Lm. This one is m times f of x minus L, and this one is like g of x minus m times f of x minus L. Okay, hopefully that's relatively clear. Okay, what am I doing? I'm just drawing like a picture of the relationship between f times g, L times m, and if we're thinking of like, okay, if we're thinking of, let's talk this out a little bit better, right? Because what do I know? I know the limit as x approaches c of f is L. So near c, we expect f to be like almost L. So what's f of x minus L? F of x minus L is this tiny, tiny little gap between the function and L. And it's this f of x minus L which is supposedly like infinitely small or something, right? Built into the definition of what it means for the limit as x approaches c of f to be L is that the gap between f and L can be made arbitrarily small. So in other words, I can make f of x minus L as small as I want by taking a really, really tiny delta. Okay, so you should think of this as being, you know, sort of like really, really tiny, this thing I just wrote in here in red. And similarly, the limit as x approaches c of g is m. So in other words, I can make the gap between g and m very, very, very tiny as well. And so as small as I want. And so I should think of this, now I'll do it in green, thing is also really, really tiny. And okay, and it's Lm that is pretty big. So in fact, all three of these are very, very, very small. Okay, good. So, this limit here, I'm going to underline this in red. This is this limit that I'm trying to show is 0, right? Okay, well let's get a better handle on this whole f of x minus Lm thing. Okay, so just like the expression fg minus Lm is indeed just equal to, well, look at the picture. Take f and g and subtract the Lm rectangle from it, and what you get is these three other rectangles. So this just is L g of x minus m plus m f of x minus L plus f of x minus L g of x minus m. So what have I just done here? I've just used my picture to express the difference between fg and lm as a sum of three things. But I haven't actually used geometry in any crucial sense. I used geometry as the inspiration to write this algebra in the way that I have, but the algebra stands on its own. By that I mean, if you just simplify the right-hand side of this equation, you will get the left-hand side, right? Because look, here we get like an LG, but then that LG gets canceled out by this minus LG. And here we get like a minus LM, but here we get another minus LM, but here we get a plus LM. So minus LM plus LM leads to a minus LM. And then we get an MF, but then that gets canceled out by a minus FM. And am I just done? Yeah, and then of course I get like an FG. So okay, I think I've just shown to you by talking it out that if you multiply out the right-hand side, you get the left-hand side. So I use the geometry merely to think to sort of to come up with this crucial algebra fact here, which is really kind of going to do all the work. And now, finally, I see what my real goal should be, which is I need to show that this is 0. So that means what I really need to prove is that the limit as x approaches c of, and now I'm going to put sort of giant brackets, L g of x minus m plus m f of x minus L plus f of x minus L times g of x minus m is 0. If I can prove that this giant thing is 0, then I will be done, because that will have established this fact, which is equivalent to the thing I'm trying to prove. But here's the thing. I don't have space to write this whole thing out, but applying the lemma once again, since the limit as x approaches c of f is L, that means that the limit as as x approaches c of f minus L is 0. So this, maybe I do have a little, well, I don't really want to write this out, so I'm just not going to. This goes to 0. What I now propose that we do is, what I now want to do, but I'm not going to write it down, I'm just going to talk it out. And by the way, this is why it's kind of worth it to prove this limit law 1, which says that constants are not important. Because what I now want to do, but I have finite board space, so I'm not going to write it out, is what I'm now going to do, in order to show that this is 0, first, I'm going to apply limit law 2. What does limit law 2 say? It says that this limit is just the sum of these three individual limits. So, split this up into this one, plus this one, plus this one. Great. Okay, what is the limit as x approaches c of L times g of x minus m? Well, I am also allowed to just pull out an L. Okay, great, do that. What is the limit as x approaches c of g of x minus m? Answer, it's 0. Because by the lemma, the limit as x approaches c of g is m, so the limit as x approaches c of g of x minus m is 0. Okay, so without writing it all out, this becomes L times 0. This becomes m times 0, and I'm just left with this. Therefore, there's really only one thing I need to prove. The actual thing that I have to prove is that the limit as x approaches c of f of x minus L times g of x minus m is 0. If I can prove that this third term is 0, then since I know that this one is 0 and this one is 0, by limit law 2, the sum of all three of them is 0, but that shows that, that this limit is 0, which shows the thing I want. Okay, so now with the little board space left, we finally get to kind of begin the proof or something. How can I show that this limit is 0? Well, what's going to happen? I'm going to get challenged with an epsilon. So what I need to show is that for all epsilon greater than 0, there exists a delta greater than 0, such that for all x, and now what's going to happen? I'm going to get close enough to x, delta close, such that, okay, and now it's going to be really hard to sort of write this, but basically I need, I need the difference between my function, which is this product, and the limit, which is just 0, to be less than epsilon. So okay, so maybe it's not that hard, right? I need absolute value f of x minus L times g of x minus m to be less than epsilon. Okay, so that's what I need. Well, doing like a tiny little kind of discovery phase over here, or maybe I won't even bother. Yeah, maybe I won't even bother doing a discovery phase because I don't have really room for it. What would it take to show that this product is less than epsilon? Well, okay, well maybe we begin the proof. So begin proof. What is the first thing that happens? The first thing that happens is we receive an epsilon. So take arbitrary epsilon greater than 0. And now I have to figure out how to respond, right? I have to figure out what delta to respond such that this product is less than epsilon. How can I make this product less than epsilon? Well, one way to make this product less than epsilon is if each of these were less than square root of epsilon. But of course, I can easily make each of these less than the square root of epsilon because the very fact that the limit as x approaches c of f is L means I can make f of x minus L as small as I want. And I can make g of x minus m as small as I want. So, so this is what we do. We say, maybe I have room for this. So since the limit as x approaches c of f of x is L, what we're going to do is we're going to challenge. And we're going to challenge, trying to decide where to write. We're going to challenge it, so challenge it with the square root of epsilon. And then you're going to receive some kind of answer, and the answer is delta 1. What is delta 1? Delta 1 is how close I have to get to c such that the gap between f of x and L is less than the square root of epsilon. Epsilon's a tiny number, so the square root of epsilon is also a positive number. And so what do I know? What I know, therefore, writing very small, is that if I am within delta 1 of c, then the gap between f of x and L is less than the square root of epsilon. And then again, since the limit as x approaches c of g is m, then what I'm going to do is I'm going to challenge it with the square root of epsilon again. And I will receive a different number. And what I will receive is delta 2. What is delta 2? Delta 2 is how close I have to get to c such that the gap between g and m is less than the square root of epsilon. And so now what I know is that if I stay pretty close to c, specifically within delta 2, then the gap between g of x and m is less than the square root of epsilon. Okay, now finally, I'm ready to respond. And here's my response. Just like before, I'm going to set my delta to be the minimum of delta 1 and delta 2. Delta 1 is how close I need to be to C so that the gap between F and L is less than epsilon, is less than square root of epsilon. Delta 2 is how close I need to be to C such that the gap between G and M is less than the square root of epsilon. So therefore, I'm going to get close enough so that I'm within both of those intervals. And now, I'm just going to prove to you that it works. So, in this tiny little spot, I'll sort of just like finish off the proof. What must I show? I must show this conditional, right? So I'll take this delta. So assume that the difference between x and c is less than delta. But if it's less than delta, then it means that we're less than delta 1 and also less than delta 2. So we're less than delta 1 and the gap is less than delta 2. And so what do I know? By applying this conditional, I know that the gap between F and L is less than root epsilon. And by applying this conditional, I know that the gap between G and M is less than the square root of epsilon. And now I simply multiply these two facts together. And that tells me that F minus L times G minus M is less than epsilon, and that is exactly the thing I'm trying to prove. Okay, so I sort of win. I win because I've proven this conditional. I started pretty close to C, and I showed that the product of f of x minus L and g of x minus M is less than epsilon, because each of these is less than the square root of epsilon, so their product is less than epsilon. And I made each of these less than square root of epsilon because I knew that these two limits existed. And so having proven this, just to kind of reiterate, having proven this, what have I actually proven? I've proven this. That this limit is 0. And since this limit is 0, and I already knew that this limit is 0 and this limit is 0, then the sum of all three of these must be 0. But the sum of all three of these is just this. And so I have now shown that this is 0, and by the lemma, that shows that this product is Lm. And so we are done. Woo! That completes this optional video series on low-level limit laws. Hopefully you enjoyed it. Goodbye.